No. Cool. So we will listen now to Arthur Jacot, who is a PhD student with Clément Angler at EPFL.
Hello. Okay, you can see the slides. Okay, great. Okay, so so today I'm going to talk about some regimes of training, and especially trying to understand what happens in terms of the loss landscape, because what's interesting is that we'll talk about two regimes. One regime, which you know, maybe some have heard, is this anti-cake type of results, which is characterized by a loss landscape where you don't see any saddle. You actually converge very fast to a global minimum and don't see effect of saddles. And then I will talk about another regime, which is the opposite, where you actually move close to a sequence of saddles during training. And what's interesting is that you can, for example, in the talk by Burfin yesterday, she was talking about how increasing the number of neurons could lead to a higher proportion of global minimum to saddles, for example, or what Shoria talked about just before about how changing the loss surface could lead to different ratio of saddles and different disposition of saddles and global minimum. Here in this case, what's interesting is that you have actually the same loss, but depending on the size of your initialization, you will end up in either a global minimum dominated regime or a saddle dominated regime. And you can also observe, you can even observe this transition in the infinite width limit. So let me just shortly define what type of neural networks I'm going to talk about. So I will talk about deep neural networks, deep fully connected neural networks with layers numbered from 0, the input, to capital L, the output, with each layer containing NL neurons. And I will consider, just for simplicity, neural networks without bias. So in this case, then the network function, so the function that maps the activation of the inputs to the outputs, is just a sequential composition of weight matrices and then entry-wise nonlinearity. And and I will call the set of parameters theta the concatenation of all of these weight matrices. And I will talk about very large networks, and typically it will mean increasing the width of the network. So considering rectangular networks where the number of neurons in all of the hidden layers is equal, and then let this W, this number of neurons in all of the hidden layers, grow to infinity. Also, when it comes to this second result, it's a result that we only showed for linear networks. So linear networks is when you take when you don't have any nonlinearity, or just take the nonlinearity to be the identity. And in this case, the network function is going to be a linear map, and so a linear map can be represented by a matrix. And in this case, the matrix is just the composition of all of these weight matrix W1 to W capital N. So now, of course, today these 2 days we have to talk about the loss surface. So in the setting I consider is when you have a finite training set of size capital N of inputs and outputs, and we consider the mean squared error, which is the average, the usual mean squared error. And of course, we want to optimize, understand the dynamics of gradient flow on this loss, and to be able to optimize these parameters. And something that has been observed again and again is that just taking a random initialization of the parameters and using gradient descent, you're able to, as long as the network is wide enough, as long as you have enough neurons, everything works well. Gradient descent is able to find a global minimum. But that's something that we don't completely understand, because we know that this loss is non-convex, so it's not obvious why there's no issues in this strategy. And one thing I want to talk about is that when talking about non-convexity of the loss surface, often people show a picture of what some kind of generic, what could be a generic non-convex loss, for example, these spin glass losses, where you have lots of different isolated local minimas and saddles. And I want to emphasize the fact in this talk that the loss surface of neural network is really non-generic in its non-convexity. The three properties which are kind of non-generic, the first one that was already mentioned in previous talks is the aspect that when in this overparameterized regime, when the width is very large, instead of having isolated global minimum, you can see some kind of manifold of global minima. And the dimension of this manifold is going to be roughly the dimension of the parameters minus the number of data points, essentially the degrees of freedom minus the constraints, the rough dimension. So it's going to be a very high dimensional manifold, but inside an even larger dimensional space. So it can be quite difficult to understand the structure of this manifold. That's kind of what we would like to understand, is the geometry and structure of this manifold, but it's quite difficult to visualize because it's such a high dimensional object. And some other non-generic properties of neural networks is the loss of neural network is that we have some non-strict saddles. So these are saddles where the Hessian where the Hessian is has no negative eigenvalues. And for deep networks, you can find such a non-strict saddle at the origin. So when you set all the parameters to 0, and this non-strict saddle is going to play a role later on. And another also specific properties of neural network is the fact that the saddles also form into manifolds. That's what Burfin talked about yesterday, right? That you could construct this kind of manifolds of saddles too, which are also high dimensional. And that's again something quite non-generic in neural networks. And so I want you to, today, I really want to try to give you some intuition about especially this manifold of global minimum, what this loss looks like, but it's quite difficult to visualize. So there's one setting where you can actually see, in a sense, this, can easily observe this manifold of global minimum. Basically, what you can do is that if you take only one single training point, then the dimension of the manifold of global minimum is going to be the full dimension minus 1. And so if you take a random plane in parameter space, it will intersect with the manifold of global minimum as a sequence, as a union of different lines. And you can see this intersection. So here on these plots, you can see the manifold of global minimum intersected on this random plane of the loss surface. You can see these are these dark blue lines that you can see. Here you have 3 sets on this plot on the left, and here you have 2 lines on the right. And when you look at this manifold of global minimum here, I mean, it's just, of course, this is just the intersection of the manifold of global minimum with some plane. I think an interesting property is to see that there's regions which are close to the origin. The origin is this black dot, but then you have these diverging valleys actually. So of course I had to stop at some point computing the loss, but of course these valleys actually continue towards infinity and diverge towards infinity. And you can really see that actually if you look at the valley around this global minimum, it becomes more and more narrow the further away you go from the origin. So that's one of the features I want you to keep in mind for the rest of the talk. And the other feature, which is also interesting in this picture, is that you can see that there's some kind of flat region around the origin, so in the middle. And so basically, today what I want to explain to you is that depending on how you initialize your network, you will see a phase transition where either your initialization is inside, for small initialization, you initialize in this flat region, or for large initialization, you initialize far from this flat region and actually end up initializing inside of these narrow valleys, and you get completely different training dynamics. And one kind of heuristic that can suggest this when this transition happens is the following proposition that we showed in a recent paper. So what we consider is, so this result is at the moment only for linear networks, but I'm already working on generalizing it to non-linear networks. So what we consider is we take a random initialized parameter, initialize with the variance given by w to the power minus gamma. So gamma is going to be the scaling of the variance, and we're going to let w grow. We're going to consider large with w's. And so if gamma is small, it means it's going to be a large initialization. And if gamma is very large, it corresponds to very small initialization, because as the width grows, the variance goes to 0 very fast if gamma is large. And we are only considering initialization which are not too large. So when gamma is larger than 1 minus 1 over L, because that's if you take any larger initialization, actually the variance of the network function at initialization would explode to infinity. So that's kind of all of the viable initialization. And the two quantity that we are interested in to try to understand whether we are in this global minimum dominated regime or saddle dominated regime is the distance between the initialization and the closest global minimum, d mean, and the distance d saddle between the initialization and the closest saddle. And what we observe is a phase transition where we have a large initialization where gamma is smaller than 1, where the distance to the closest global minimum goes to 0 as the width grows, because we obtain rates of this, so stochastic rates of this distance. And we see that these rates, of course, the exponent here is negative. So as the width grows, the distance to the closest global minimum goes to 0, whereas the distance to the closest saddle instead increases as the width grows. So that's clearly a regime where you initialize very close to a saddle, but very far from, very close to a global minimum, sorry, but very far from any saddle. And as I will explain later on, this is this NTK regime that you can study, or lazy regime or kernel regime that we studied in that we described in 2018. And this regime is going to be very well behaved because you're initializing a valley which is very close to a global minimum, and so the dynamics become actually very simple. On the other hand, if you take a small initialization, you initialize on this flat region in the middle. And what you see here is that the distance to the closest global minimum remains of roughly constant as the width grows. So you don't get closer or further away from the global minimum. However, you initialize closer and closer as the width grows to a saddle, because here you see this negative exponent of the width here. And so maybe just to mention here, also some people have talked about the mean field regime. The mean field regime would be the critical one when gamma is equal to 1, essentially. And in this regime, the distance to the closest saddle and closest global minimum both are constant. So in this regime, that's it's not clear whether you would be the training is going to be dominated by saddles or global minimum. But in this presentation, I will only talk about these two different phases. So gamma strictly smaller than 1 and gamma strictly bigger than 1. And so before I give some theoretical result about, explain go through the theoretical result that we have about these two settings, I want to give you some visual intuition of what's going on. And so we take the same picture. So again, just one training point. So the same picture I presented 2 slides ago. And I'm going to take 2 initialization, one large initialization in red here, which corresponds to a gamma of 0.5, which is clearly in the larger initialization regime, and a small initialization with gamma is equal to 2.4. And you can see, as I said earlier, that you can see that this red regime is going to initialize in this narrow valley that diverges towards infinity. And it's going to initialize very close to a global minimum here, and converge very fast towards it and stay inside of this narrow valley. On the other hand, for this small initialization, you initialize close to the saddle, which is located at the origin. And at first, for some time of training, it takes a long time to escape this first saddle before converging to a global minimum. And so you can see, if you look at the loss, you see that the loss starts with a plateau, because you're affected by the saddle at the origin for some time before escaping the saddle and converging to a global minimum. And what's interesting is that you clearly see that you end up in some very different, you also end up in some very different regions of the manifold of global minimas. Of course, if you were to take even larger width, then actually the distance, the difference between the red line would be even further away, even further into this narrow valley region, because the distance between the two grows as the width. The difference in scale between the two regimes scale grows up with the width. So that's the kind of picture that I want to have you to have in mind. And so now I'm going to talk about theoretical result for this red line, for this red training path, and this, and then in a second part for this the green one. So for the red one, it's the central object to understand this large initialization regime is really the neural tangent kernel that we introduced in 2018. So the neural tangent kernel is is a kernel. So you take two inputs that live in the input space, right? And you compute just the scalar product of the gradient of the output of the network at x and y with respect to the parameters. And this neural tangent kernel plays an important role if you want to describe the evolution of the network function f theta in time. So if you want to know, as the parameters follow gradient flow on the cost, if you want to know how the output of the network function at a point x evolve, you get a formula which involves the NTK, which is a sum over all training points, and essentially the NTK tells you how much the training training point xi is going to affect the evolution of the network function at another point x, in a sense. And basically, if we are able to describe this term, then the difficulty in understanding this differential equation is really to understand how this term behaves. And the problem is that this term, at initialization, this NTK is a random object because it depends on the parameters which were sampled randomly. And then during training, the parameters evolve, and so the NTK is going to evolve as well. But what we showed is that as the width grows to infinity, this NTK converges to a deterministic and fixed limit with some rescaling because it's a slightly different setting than in the original paper. So this was a result that we showed in one specific case, which is equivalent to taking gamma to 1 minus 1 over L. So this was the largest possible initialization in a sense. But some more recent results suggest that, suggests that actually this convergence of the NTK to a deterministic limit should extend to the whole large initialization regime I talked about. So any gamma which is strictly smaller than 1. And what this, and essentially the reason why the NTK is fixed during training is really because of the fact that you converge to a very close by global minimum that I mentioned before. And because you move so little, actually, because there's a very small change of the parameters, that's why the NTK doesn't change much. And the implication of this convergence of the NTK is that you get some very simple linear asymptotic dynamics where the evolution, now we can just take the same differential equation, but replace the NTK by this limiting NTK, which is a constant object. And now the differential equation for the network function is just a linear differential equation, right? Because this term on the right depends linearly on the network function itself. So you can solve this, this differential equation and get very precise description of the network function at any time t. As I already mentioned, what's also interesting in this regime is that you converge to a very close global minimum. Actually, in this infinite width limit, you do converge to the closest global minimum. I think in the previous talk, it was already mentioned, this aspect. And so, another also interesting consequence is that, so you initialize, actually what's kind of surprising is that you have these diverging narrow valleys and you randomly end up initializing inside of these very narrow valleys, very close to a global minimum. And because you move so little, if you look at the loss around the training path that you take from initialization to this global minimum, you can show that the loss is going to look almost quadratic. And so that's a plot typically where you see the level lines of the cost of a large neural network are ellipses, look like ellipses, so it suggests that it's almost quadratic. And this explains why you get such fast convergence. So that's the NTK regime. And now let's go to this other regime, and we will observe some completely different dynamics. So this result is only for linear networks at the moment. But generalizing to nonlinear networks is quite a hard task, of course. But so in this case, we're studying, actually, it's not a study of the whole small initialization regime. It's only the extreme case. So when gamma essentially goes to plus infinity, so the smallest possible initialization. And what this means is that we take a gradient flow, which is initialized at some positive scalar alpha times some random initialization. And then, so we fix this theta 0 and then let alpha go to 0. So essentially we take an initialization that vanishes. And of course, if you just try to look at what's the limit as alpha goes to 0 of this gradient flow dynamics, you will see nothing, because there's a saddle, as I already mentioned, there's this non-strict saddle at the origin. It's non-strict because actually the first L-1 derivatives vanish. So if you're in the deep case, the Hessian is just 0. So, and even the higher order derivatives vanish. But so you have this saddle at the origin, and the closer you are to a saddle, the longer it takes you to escape the saddle, right? And so if you just let alpha go to 0, the limiting dynamics, nothing happens. You just get stuck at the saddle. So to study these dynamics, what you need to do is that you need to study the dynamics after some time t. You have to give it enough time to escape this first saddle. And so we define what's and describe what we call escape times, T alpha. So T alpha is a time which grows as alpha goes to 0, and it's essentially the time it takes to escape this first saddle. And then we look at the limit of this gradient flow path as alpha goes to 0, but after escaping the saddle. And what we show is that this dynamics converges to what we call an optimal escape path. So an escape path would be any gradient flow path that leaves the saddle. And this path is unique in the sense that it's the fastest, it escapes this saddle at the origin the fastest possible. This is kind of a formalization of maybe some intuition that you may have, that if you initialize very close to a saddle, you will naturally escape the saddle along the direction which escapes the fastest. And this is just, so to prove this, of course, there's some more technical details, especially for this deep case where you have this non-strict saddle, in which case it's quite difficult to identify these optimal escape directions and really show that you actually follow these escape paths. And one thing which is really nice that follows from the structure of neural network is that this optimal escape path is unique up to symmetries. So here for linear networks, there's a bit more symmetries than just these permutations that were already mentioned in previous talks. In linear networks, the symmetries, you can also take any rotation, any orthogonal transformation of the hidden layers, right? So this optimal escape path is unique up to symmetries under some assumption, of course. And what's interesting is that essentially this escape path lies inside of an invariant region. So it's some kind of manifold, some kind of region where if you initialize on this region, you cannot escape this region. And this region is characterized by the fact, not characterized, but has the property that if you take any point in this invariant region, the rank of the matrix represented by the network is going to be 1. And so it implies that the rank of the matrix represented by this, by the parameters at any time on this optimal escape path is always 1 for all time t. And so what this implies is that the gradient flow, which was initialized close to the saddle, is going to follow this optimal escape path. It's not going to be exactly on the optimal escape path, but very close to it for finite alphas, but finite but very small alphas. And another consequence, what's also interesting is that where does this, the obvious question is where does this optimal escape path ends up? Now, the thing is that because it's constrained to only represent matrices of rank 1, it can never reach a global minimum. Because, of course, except if on some very specific, very strange losses, in general, if you have a loss, you wouldn't have a global minimum which has only rank 1. So essentially, what happens is that this optimal escape path converges to a point which is optimal amongst rank 1 matrices, which locally minimizes the cost amongst rank 1 matrices. And so, but this point is going to be, so it's going to be a critical point of the neural network, but it's going to be a saddle actually. And so gradient flow because this optimal escape path converges to this rank 1 saddle, it implies that also this gradient flow initialized, this theta alpha, also comes very close, approaches the same rank 1 saddle. And so that's where our theoretical analysis kind of, we have a small issue because essentially we could try to use the same results to understand how you would then escape, because we are kind of in the same setting. Now we are approaching a different saddle. And so you would expect also to escape this second saddle along an optimal escape path again. But because because of technical issue, it's kind of difficult to understand how you approach this next saddle. And so we cannot prove that the same thing happened, but we conjecture that essentially the proof goes through and that this doesn't cause any issues. And so our conjecture is that essentially in this dynamics, in the limit, gradient flow is going to visit a sequence of saddle of increasing rank. So starting from the origin, which is essentially a rank 0 saddle, going to this rank 1 saddle, gamma 1, then following an optimal escape path to go to a rank 2 saddle, and so on and so forth, until it finally reaches a global minimum. And yeah, so you clearly see that. So what we also conjecture is that, and that's something that we observe empirically, is that this type of dynamics extend to this whole small initialization regime. So as long as gamma is strictly larger than 1. And you can really see that in this regime, you have a completely different dynamics, where the dynamics are dominated by this saddle that essentially that's forced. Essentially, when you initialize close to a saddle, you're forced to go to a second saddle afterwards. And so let me show some plots to help you visualize what's going on. So when you take this initialization, so that's for a very small initialization, that's the train and test error in time. That was for a matrix completion cost, which is slightly different than the mean squared error cost. So it's, you take a matrix, then in this case a 10 by 10 matrix, and which is low rank, and essentially you observe only 70 entries of the matrix, and you want to recover the last entries of the matrix. And what you see here is that there is this plateau. So because you start close to the saddle at the origin, you get stuck at the origin. So that's explained this first plateau. Then you have this short, you drop down to a next plateau. So that's in this short time, that's when you jump from one saddle to the next. You get stuck at this second saddle here, which you escape again to go to a third saddle before converging to a global minimum afterwards. And you can really see, so that's a plot of what's going on in parameter space. So a projection of the training trajectories in parameter space to a 2D plane. And so what we have here is we have the origin here with the saddle at the origin. In blue, you have this optimal escape path that converges to a second saddle, omega 1 here. Then from this saddle, we have this optimal escape path of the saddle that converges to a third saddle and fourth saddle. Sorry, and then finally to a global minimum here, each time with this optimal escape path. And you can see that essentially for finite alpha, you can see that the path of gradient flow kind of follows this sequence of saddles. And also on the right, you can see if we plot the train and test error of each of these three paths, we see that we really recover the same drops exactly. In a sense, the only aspect that we, at the moment, we don't have so much control on is exactly how long you stay on each of these saddles. So that's why I put this kind of 3 dots, because essentially as alpha goes to 0, you will stay longer and longer close to each of these saddles. But when it comes to what happens between the saddles, you see that we have essentially that this drop here is exactly the same drop as this one here. And so, so maybe to try to come back to this first picture I gave you about this loss surface. So the idea is that this is what happens on this flat region close to the origin. Now, of course, the flat region that I showed you in the first example was kind of too simple because there was only one training point. So you had this flat region and it will drop straight down to a global minimum. When you have more data points, or for example, in such a matrix completion setting, it's a bit more complicated. So here you have this saddle at the origin with this flat region around it. And you see that it converges to this second saddle here, which is also in a flat region, in some kind of flat valley that you see here. And then it escaped this flat region to converge to a global minimum. So it's a slightly more complicated picture than the one I showed you at the beginning, because the first picture was kind of too simple because we had only one data point. There's some kind of hierarchical structure where you have essentially layers of plateaus that you drop from one to the other before converging to a global minimum. But still, you get this picture. And what's also interesting is that in this picture is that you can also see that essentially when you escape the saddle, there's some kind of notion of breaking the symmetry. because as I said, the optimal escape path is only unique up to symmetries. And so there would be actually, you can see here, it's actually another global minimum, and there would be another optimal escape path that would instead escape on the right instead of escaping on the left. And so in a sense, the reason why it takes time to escape this saddle here is that you have to break the symmetry to choose towards which global minimum gradient flow is going to converge. And that's a very, I think, a very important concept in this setting. Okay, so to summarize, I talked today about two regimes, which depends on the size of the initialization. And what's interesting is that actually, even on the same loss, you don't have to change the loss to observe these different regimes. You just have to initialize in different regions. And first, for large initialization, we have this NTK regime, which is where you essentially see no effect of saddles, and you converge very fast to a close by global minimum, and dynamics can be are asymptotically linear. And then for small initialization, a saddle-to-saddle regime, where instead that's the complete opposite. You see a very strong effect of saddle, where you jump from saddle to saddle, and each of them lead to some plateaus in the loss curve. So actually training can be very slow in this regime, in contrast to the NTK regime, where training was very fast. But at the same time, what's interesting in this saddle-to-saddle regime is that you get some kind of natural sparsity result, because essentially what the network is doing is that it's first trying to fit the data with just a rank 1 matrix, then a rank 2 matrix, and so on and so forth. And it stops as soon as it's able to fit the data with a low rank matrix. So you see this sparsity effect. Thank you.
Thank you very much, Arthur. So we have two questions in the Q&A for you. Maybe you can read them.
Yeah. Does this mean that for every such linear network, there is only one flat region in the landscape, and that one is around 0, along with many narrow valleys far from 0? So yes, I think that, I mean, of course, as I shortly mentioned here towards the end, there's this kind of, there's more than one flat region. There's the flat region around the origin. And I think that it's, you can only see essentially this, this is the flat region which has the same loss as the 0 matrix in a sense, but then you have these other kind of flat region which are at slightly different point. But I think that yeah, and maybe something that I forgot to mention, I mean, which I also kind of mentioned, is that this saddle at the origin is connected to a manifold of saddle which extends to infinity. So actually this you could say that in a sense this plateau also is connected to infinity. But it turns out that when you are far from the origin, so in this region far from infinity, there's more global minimum than saddle, and so maybe that's why you only see it dominating close to the origin. Now, do you expect the same pattern on one flat region and many narrow valleys to hold for nonlinear networks? So that's, I think, so actually this first picture I forgot to mention it on the right. That's for a nonlinear network. So you see a very similar picture. And I think that basically the fact that the NTK regime is related to these narrow valleys in nonlinear networks, that's kind of clear now. Now, understanding these flat regions, I mean, we know that you can also find a saddle at the origin in nonlinear networks, and that's what I'm currently studying. So I think that this general picture should extend to nonlinear networks. Next question. So is the saddle-to-saddle dynamics, saddles of increasing rank and progressively visited, related to the result presented yesterday by Tijin 2, that through the training the networks behave as one with progressively more nuance? So yeah, I think that in a sense this saddle-to-saddle dynamics is kind of a proof of like a theoretical result showing what was expected by Tijin in this linear regime. And essentially, I think that the extension of this result to nonlinear case would look a lot like what Tijin was talking about yesterday. So next question. Great talk, thank you. Since small initialization is slower, why in practice we initialize with small weights? Is it for implicit regularization, similar to what we saw yesterday? So actually the typical initialization, so the Lequin initialization, for example, it's a small initialization because it corresponds to, in a sense, it corresponds the local initialization kind of corresponds to gamma is equal to 1 minus 1 over L. But the thing is that it's still a positive gamma, right? So it still means that the variance goes to 0 as the width grows. So in any case, you will always consider small initialization, because if you didn't took initialization that vanishes as the width grows, you would get a variance that explodes at initialization. So yeah, I think I think that's so next question. What you present with respect to saddle in the small initialization regime sounds similar to what Zikin presented about the can you draw a connection to like so basically I think that's similar to the previous question, right? So
thank you so much. Marco, do you want to ask your question?
Yeah, sure. So adapt two. I mean, one is, so you have this nice picture where you go from saddle to saddle and then they become increasingly low rank. Can you say anything a bit more quantitative, like how many times do you switch, how long do you stay, or is this insanely hard?
No, so basically in linear networks, that's kind of what's quite different from the non-linear case, is that you really increase one rank by one. So it's really incremental each time, one more. I mean, of course, you need some constraint. You need to take the gradient, and you need to assume that because essentially the direction along which you escape is related to the largest singular value of the gradient at that point. And so, of course, you need to assume that there's this largest singular value is unique, right? That is, it's not. It has multiplicity 1. Otherwise, you could increase by 2 at the same time. But it's in general, it's kind of you wouldn't expect to have multiplicity more than that. And basically, no. So we do have some information about the time it takes to escape. Basically, how they scale with alpha. In the shallow case, basically the escape time this escape time T alpha grows as log minus log of alpha, and for the deep case it's different. It's actually alpha to the power capital L minus 2. No, sorry, alpha to the power negative capital L minus 2. Yeah.
It's faster.
Yeah. Wait, yeah, that's sometimes kind of a little bit confusing to understand what's faster or not, because
yeah, so log 1 over alpha is shallow, and poly 1 over alpha. So alpha is small, right?
Yeah, alpha goes to 0.
So it's slower. So it's faster if it's shallow. Wow, that kind of makes sense, I guess.
Yeah, it makes sense.
Parameter, so it's hard.
Yeah, and in general, so that's for deep case. So you see that these drops are very sharp. For shallow networks, the drop are a bit smoother in a sense.
Cool, nice. I have some more, but I'll ask later, so that I won't dominate.
Giulio, you had a question. Is it still the case?
No, I had the same question, so it's fine.
Okay. So Surya?
Oh yeah, just a comment actually. Like it's a very nice talk. We saw kind of similar results, we didn't prove it at the level of generality that you proved it, but when we looked at exact solutions to the learning dynamics of deep linear networks, we saw from small initializations for specific initial conditions, you get the saddle dynamics, and the timing of the drops in both training and test error depend on the data, of course, because the data determines the loss landscape. And the time is simply 1 over the singular values of the input-output correlation matrix of the data. And so there's a nice connection there between the timing of these drops and the data structure.
Yeah.
And basically what the network learns after it passes each saddle is a particular singular mode of the input-output correlation matrix of the data.
Yeah, I think that's in this setting where, right, for mean squared error loss, when you have some kind of alignment between the.
That's right. That's right.
Yeah,
so we didn't have the general results. So.
Yeah, I think that basically what you mentioned, I think it's like, so we are able to describe how it scales with alpha, but not the constant in front of this log term and log of alpha. And I think that's what you mentioned are basically the constant in front in a sense, right?
Right. In some other work, we observed that, you kind of, so the question is, what's the right scale of initialization to minimize test error, right? And what we see in nonlinear networks is there's kind of 2 competing constraints. You want small initialization because in an over-parameterized setting, the initialization doesn't contain anything about the true function. And without explicit regularization, you don't forget the initialization, so it can only hurt you in terms of test error. But for very small initialization, you run into the vanishing gradient problem. At large initialization, you have you're in a regime where you have a very chaotic landscape, and also you have exploding gradients. So kind of initializing at an intermediate regime empirically achieves the best test error. But I'm wondering where the intermediate regime lies in relation to these two extreme regimes you look at.
So I think that at least for the this matrix completion case, basically the smaller the initialization, the stronger this lowering bias you obtain.
Yeah, that's right.
And so actually it's always better to take a small initialization, except for the fact that the training is going to take an increasing amount of time, because it's going to take you longer and longer to escape the saddle. So in a sense, in this setting, I would say that the trade-off is more between generalization and convergence speed.
And yeah, that's right. Yeah, that's what we saw too. Yeah, but I think I don't know if for deep nonlinear networks, whether we're already hitting the point at which a further reduction in the initial variance would lead to unacceptably long training times.
Yeah.
I'm just not sure where industry is sitting on that trade-off.
Yeah. But at the same time, it seems that, I mean, the typical initialization, like Lequin is actually more in this, it should be normally in this NTK regime. Of course, for finite width, it's less clear where the transition exactly is.
That's right.
But yeah.
Okay, thank you very much, Arthur. So we will do a 35-minute break, and we will be back at 5:05 for the remainder of the